Hello, and welcome to our monthly guest lecture on coffee and cocktails. I'm your host, Dr. Ann Wands. We have the pleasure today of listening to Mary McIntyre, Fellow of the Royal Astronomical Society, who will be talking to us about shadows in space and the stories they tell. But rather than ask what drink you're having for the show, Mary, would you like to begin? But before you begin, I would like to show how excited I am about my little Halloween trinket, which is the skull, the wax skull. It's all we've got to celebrate Halloween, but I want to wish you all a happy Halloween, one of my favorite holidays. In fact, it's one of Mary's favorite holidays, but I will let her get to that right now. In fact, I'm going to make her host, and I'm going to stop talking.
Yeah, I think I prefer Halloween to Christmas, but that's probably not everyone's view. Okay, I'm going to share my screen and get started. So welcome to my presentation, which is one of my favorite presentations out of all of the ones that I do. And the idea for this came about, first of all, when I started learning how to do lunar sketching. And one of the things I look for when I'm choosing something to draw on the moon is a feature that has really defined shadows and really defined highlight regions. And that could be a crater under the correct moon phase, could be a mountain range on the moon that's casting shadows. But when I started doing this, it got me thinking, what can I learn by studying these drawings and the pictures of the shadows? And it turned out that we can learn an awful lot by studying those shadows. So I'm going to go through some of that today. We'll be coming back to this particular crater in a moment. But first of all, let's just begin on Earth. Here on Earth, we will all be familiar with our shadows on sunny days. Not always many of those in the UK, especially not in the northern UK where I'm originally from. These particular shadow pictures were taken during the solar eclipse in America in 2017, but we see shadows any day that the sun is out, basically, and we'll all be familiar with that. Now, one of the things you can do by studying shadows here on Earth is to calculate the height of something that's really tall. And I'm using the example here of Canary Wharf. So let's just pretend Canary Wharf is not surrounded by a sea of other buildings, and we can get a clear look at its shadow. And if we measure the length of Canary Wharf shadow, this is just a worked through example. One of the figures you might get at this particular time of day is 270 meters for the length of the shadow. If you take something of a known length and measure the shadow as well at 90 degrees to the ground, for example, a 1 meter ruler, which on this diagram is not to scale because obviously Canary Wharf is taller than 4 of those. But if we take a 1 meter ruler and measure the length of the shadow of that, we could get something around 1.15 meters. Now, it's important when you do this that you measure both of the shadows at the same time of day from your location, and I'm going to talk about why that is important in a second. But we can do some really simple maths here because, bear with me, maths is not my strong point, but no, this is quite straightforward maths. We know the length of this 1 meter ruler, we know the length of its shadow, and we know the length of the shadow of the tall building. So we just divide one by the other to find out the height. So we saw Canary Wharf was 270 meters. Divide 270 by 1.15 and you get something around 235 meters, which is roughly the height of Canary Wharf. Now, as I mentioned just now, it's important that you do this at the same time of the day. Now, this is a time lapse from one of our bedroom windows, and you can see the shadows here are lengthening as the day goes on. As the sun gets lower in the sky, the shadows begin to elongate. And certain parts of the world, you have a no shadow day where the sun is directly overhead at noon. And we don't have that in the UK. But it's important if you are going to do any of these calculations and measurements that you do both of them at the same time. Otherwise, your result is going to be skewed ever so slightly. One of the things you can do that's really great fun, and it's a great activity for kids, is to do a shadow stick experiment. And this is where you take, like, for example, our 1 meter ruler. It's actually my dressmaking ruler, but we use it for all kinds of things. And you just lay some tarpaulin on the ground and then at regular intervals measure the length of the shadow that that ruler has cast on the ground. And as the afternoon goes on, we were thwarted by clouds here after an hour and 45 minutes. But as time goes on, you will see that this shadow gets longer and longer. And if you look at sundials, they take this into consideration. One of the things that this helps you calculate is local noon, because time is standardized across countries. But but obviously the exact time of local noon is when the sun is at the highest point in the sky. And that is not necessarily at 12 o'clock as the clock goes. So it will help you calculate local noon, which is great fun. It usually varies by around about 15 minutes, depending where you are in the country. But it also means you can do some other maths. And one of the things that we can do is, this was taken on a particular day in September. We have a 100 centimetre ruler here, or 1 metre ruler, and at local noon for us here in Oxford, we measured that this was 88 centimetres in length. So the shadow is shorter than the actual length of it. Now, if you remember right-angle triangle maths, don't be afraid. You don't need to understand sine, cos and tan. There's just a button on the calculator that you press to do that for you. But the tan of this angle here, which will be the angle of the sun, is opposite over adjacent. So what does that actually mean in real terms? What we mean opposite here is the length that is opposite this angle. So in this case, it's the height of the feature that we're looking at. Adjacent is the one that's next to the angle that we're measuring. So that would be the shadow. So it's just the height and the shadow here. So that means you can then do some maths and actually calculate the sun angle. So the tan of the sun angle was 100 divided by 88, and that worked out that the sun angle at local noon was 48.7 degrees. If you did this again, this was the longest we managed to go before the clouds came over. At 1:45 in the afternoon, the shadow had elongated to 110.5 centimetres, and that worked out that the angle of the sun had reduced to 42.1. So as the day goes on, this shadow will get longer and the sun angle will get lower because the sun is lower in the sky. So that's a really useful piece of mathematics that we can use when we don't have the privilege of being able to stand on the surface of the moon or whatever other body we happen to be looking at and have a 1 meter ruler there to measure the shadows. So we're going to come back to that formula in a minute. Now, I've showed you a picture of me drawing a crater at the beginning of this talk, and this crater is located up here near the mountains. This is the Apennine Mountains on the moon. This is a photograph of mine, and this little crater here is called Archimedes. And I feel like I know this crater very, very well because I've sketched it several times. I've made several models of it, and I just feel very well acquainted with this crater. And one of the great things about lunar sketching is you do become very familiar with all of the intricacies of a lunar feature, and you do get to know the features really well. Now, this was a photograph taken by a friend of mine called Craig Howman, and this is my photograph of it. And when I first sketched this, it really was apparent to me that when you look at a crater normally, you would think that all of the walls of the crater are exactly the same height all the way around. But if you look at this shadow, you know that that is telling a different story. If you had somebody that's taller than you stood next to you, their shadow would be longer. And the same thing goes here. There is something on the wall here that is casting a longer shadow. Something over here is shorter. So we know that this crater wall is not uniform in height all the way around, and neither is this one because the shadow that it's casting on the lunar surface is all different heights. So without any other information here, a very, very, very crude and not to scale representation, if we were stood here in the crater looking at that wall, the skyline would be this shape. The exact height here versus distance is not accurate because we don't have any other information. But what we do know is that somehow this shadow is being cast by things that are this sort of profile on that crater wall. And equally, if we're stood on this side and looking that way, then we know that there are these little foothill kind of regions and the slump regions of that crater wall. And we know that that crater skyline would look something like this. Now, when we look at crater shadows under one sun angle, it can sometimes give you a slightly misleading picture. This is another crater called Plato, taken by one of the best lunar and planetary imagers kind of in astrophotography world, Damien Peach. Most people who are astronomers know him. And his picture of the crater Plato here is showing these really long, pointed, jagged shadows. This photograph of the Caucasus Mountains that I took, also long, pointed shadows there. And this gave rise to kind of early space artists giving these artist impressions of mountains on the moon, these huge looming structures that had really sheer drops. And it is very, very definitely true that the lunar mountains are quite tall, and they do kind of visually look taller than they would on Earth because the moon is a quarter of the size and therefore the curvature comes into play. But generally, the sides of the mountains are not as steep as this. So it's really important that you take that into consideration. And one of the things that I find fascinating, if you look at this is a trio of craters, Ptolemaeus, Alphonsus, and Arzachel. This is when the moon is about half lit, the last half of the lunar cycle, as it were, the waning moon. This is a last quarter moon. And you can see there's loads of relief here. There's loads of features visible. You've got lovely crater shadows. But that same photograph of the same region, but done during an almost full moon, all of that has been obliterated. So it's very important that when you're studying these things that you look at it under different lighting conditions, because that will tell you more about what you're actually looking at. If you look at all craters over a full moon, they all look like they're flat and they're not raised up above the surface at all. If you look at all of them under a really low lighting angle, it gives a false impression of the actual height. This is one of my favorite sketches that I've ever done, and this is my sketch based on this photograph, and just so beautiful to actually draw and amazing to just study. I made this model of Archimedes using liquid latex and latex paste, which is just liquid latex and flour. And I made this model using only the information that I gleaned from this sketch that I did of that photograph, because I know that I had to make the walls a certain height relative to each other in order to mimic these shadows. A sunrise over a lunar crater takes several hours. And then a couple of weeks later, when the moon is waning, you then get a sunset over that crater. So it's impossible to watch an entire sunrise and sunset in one go. So I made this model and I've mimicked it by moving the model rather than having the sun moving. So here the sun is getting higher in the sky on this side of the moon until it's so high that all of those shadows have completely disappeared. And then when the moon is waning, the sun is starting to get lower on this side of the moon. And then you get these shadows elongating as the sun sets over the crater. And eventually all of it ends up in shadow. And it's really cool when you just see the high regions there just still catching the light. So that kind of how. So this is Ptolemaeus again. This was the top crater of that crater trio that I just showed you the photograph of. And this sketch is based off a picture that was taken with a mobile phone, holding it up to a telescope eyepiece by my friend Dave Galvin. This was what Ptolemaeus looked like as the sun was just rising over this crater at 6:30 in the evening. And you can see there are these lovely long shadows, and lots of it is kind of in shadow and the higher bits are kind of catching the sunlight. 2 hours later, you can see that these shadows have changed a lot, and we can tell that this crater doesn't have a perfectly level floor. It's running downhill towards this crater rim here. This is really interesting because it demonstrates how the shadows are changing over time. So just to put this into kind of a visual way that's easier to understand, if we just turn this sort of on its side, the sun, the orbital mechanics of the solar system are really, really well known. And I have a tool that lets you look at the moon at any date and it will show you what the sun angle is at any part of that lunar surface. So I know that on this particular date in October 2017, the sun at 1830 UT was 2 degrees above the horizon. So it was fairly low. So we've got these long shadows being cast. But a bit later on, 2 hours later, the sun has now increased to 3.5 degrees. So it's a little bit of a higher angle. Therefore, the shadows are not quite as long. Now, we can actually use this information. Now, remember we had that little equation earlier on with the tangent. We know the angle of the sun. The angle of the sun is really well known, as I said, throughout the whole solar system. So we can rearrange that equation, and we then have opposite is the tan of that angle times adjacent. So in real terms, we can calculate the height here because we know the sun angle, and therefore can use our calculator to do tan of the sun angle and times it by the length of this shadow. So I went ahead and did the calculations on this. Now, bear in mind, this is sketches done from a mobile phone picture. So I measured the length here. Now this length and I measured the length there as well. This length is meaningless unless you know the overall size of the crater. So I'll come to that in a second. But we measure the shadow length. We know the angle of the sun in both cases. Therefore, we can calculate the height. And I'm kind of focusing on just this bit here because obviously that's the bit that's cast that shadow. So plug the numbers in. We know that this crater is 154 kilometers in diameter because all the craters are very well known. The information is out there on Google. So using that as a fraction of the overall size, I measured this angle to be 107.8 kilometers long. That's a really long shadow. So obviously the sides of this crater are quite tall. Now the sun angle, we knew that was 2 degrees. So we got a height here of the size of this crater is 3.764 kilometers. So that is pretty tall, and that is kind of about the size of many craters on the moon. You do it again here when 2 hours later, when the sun was at a 3.5 degree angle, we now have a shadow that's only 61.6 kilometers only. That's still a really long shadow. And the height there came out at 3.768 kilometers. Now, the fact that this is a sketch of a mobile phone picture and they've come out to within 0.002 of a kilometre within it, 0.004 of a kilometre of each other. That's pretty good as scientific analysis goes. Now, the actual published crater depth is 2.4 kilometres, so it is a little bit inaccurate. Now, the reason for that is because, as I said, this is a sketch, and I didn't sketch this using scientific equipment to measure it. It was just an artistic representation. It also doesn't take into account the fact that the lunar surface is curved, and the crater will not just be a uniform length all the way around, and the sides of the crater will be different lengths all the way around as well. So it's in the same ballpark. It's not out by like a factor of 10. It is kind of within the same ballpark. And bearing in mind the simplifications that we've made and the fact that if this crater was inaccurately drawn, it's been inaccurately drawn to the same amount of inaccuracy on both of them, because I was actually astonished, to be honest, when I found how closely together those numbers came out. So you can actually do the science here, and this is something that you can do on other planets as well. So you have a photograph like this. Obviously, we don't have a crater of known diameter, but what you'll need to know to do this is what field of view your camera gives you. So you will know that your camera and telescope combination may give you a field of view of 100 kilometers. So you would measure this length as a fraction of that and just work your way through. And that is pretty much how we have done this on the moon. You can do it with all of those all of those mountain shadows there all over the lunar surface, and you can calculate the height. Now, when we are looking at craters on the moon and on other planets, one of the things that is really important to keep in mind is something called the crater dome illusion. And this is best demonstrated with my cheese grater. If you look at this picture, one of them is the side of the cheese grater that has the bits sticking up that grate your cheese. The other side is flipped over so that they are recessed. Now, I know which is which here, and even I struggle to get my brain to accept which is which because it keeps flicking between the two. So the top one here is the one that is domed, and the bottom one is the one that's craters. Now keep that in mind. You know that this is domes and this is craters. Look what happens when you flip that through 180 degrees. You know these are domes, but to me they now just look like craters. And down here, these are the craters, but they look like they're sticking up. And I know they're not because I took these pictures. So as with the shadows, when you are studying things, particularly photographs from space probes, you need to look at different lighting angles because your brain can trick you into thinking you're seeing things that are just not there. This is Barringer Crater in Arizona. We know this is a crater. It's a huge crater, one of the biggest on Earth. And all I've done here is turn the image round. So when you flip it round through 180 degrees, this looks like a dome. And it obviously just isn't. It is a crater. So keep that in mind when we look at this photograph. One of these is a dome. One's a butt, they're called. It's a lava dome, which is kind of like where hot lava has caused the surface of the moon to just kind of form this little bubble. And the other one is a crater, and they're alongside each other. This is like a 500-meter measure here. And one is a crater, one is a dome. And the one on the left is a dome. The one on the right is actually a crater. And there is nothing that I can do to make my brain see that as a crater. To me, that is just always looking like it's sticking up, not down. So it's very, very important that you keep that in mind when we start to go further afield. So let's go to Mars. This is some pictures of Mars one of my friends took recently. Mars is currently at opposition, so it's in a great place to actually observe it. And I had to include this because we have rovers on Mars doing science at the moment, and the fact the rover took a selfie of its own shadow on the surface of another planet, I just think is totally cool. This is a shadows talk, so I had to include that. But as well as the rovers on Mars, we also have cameras that are on satellites in orbit around Mars. And the Proctor crater is full of sand dunes. The surface of Mars is very, very dry. There are lots of winds there, and it sculpts sand dunes similar to what we would see in the desert on Earth. This story hit the press a few years ago where they said, oh, we found trees on Mars. There are definitely no trees on Mars. I can 100% guarantee you that if anything is alive on Mars, it will be subsurface and it will be microbial. There is definitely nothing like trees living on Mars. If you look at these dark lines and you look up at the top here, you can see that this is where either a boulder has rolled down or the wind has just blown away the top surface to leave some darker material underneath. When you see it down here, they really do look like they're sticking up. It just looks like a load of tree trunks with no branches on the top, but they're very much not. They're not trees at all. I'm going to come back to the problems that gives us at the end, but I just quickly want to venture off to Jupiter. This is a photograph that my husband took of Jupiter, and this is one of the moons, Europa. This is not a photograph that we took. I wish we had, but these are very, very tiny as viewed from Earth. But we luckily have had lots of space probes exploring the solar system. Now, Europa is really interesting because the surface of it, when you see it as a whole, looks very flat. There are just these kind of scratches taken out of the surface, but the rest of it looks relatively flat and uniform. There's a region just here called Congo Chaos, and I studied this as part of a project when I was doing my OU qualifications. The whole of Congo Chaos is full of these ice rafts, and what's happened here is due to gravitational forces from Jupiter, the core of this planet, this moon, can get quite warm, and it causes parts of the subsurface to melt. So it's covered in ice, you melt, everything breaks up into rafts, gets surrounded by wet slush that then freezes again. And then that melts again and it breaks apart in a different way, gets surrounded by more slush and freezes again. And this has happened over and over and over again. So it is a very chaotic looking terrain. And it's full of these crisscross patterns, and it's absolutely fascinating to study. Now, the Galileo space probe was studying Congo Chaos and found these ice cliffs. Now, when we look at the planets and the moons around planets from Earth, we're always seeing it with the sun behind Earth, so everything is kind of uniformly lit. And as you saw from that picture of the moon earlier, that wipes out most of the features. The advantage of a space probe is that it can look at things with the sun at a different angle, so it tells you more about what you're actually seeing. And what we found during 95 and 2003 is that the chaos terrain was not as flat as we originally thought, but it shows ridges and icebergs that are around 5 kilometers around in diameter, but they can reach 100 meters in height. And these are just sheer drops of 100 meters of solid ice. And we just didn't know that that was the case until we sent a space probe in orbit around there. Similarly, when we studied Saturn's rings from Earth, Saturn has to be most people's favorite planet. It is so beautiful. But when we see it from Earth, the rings are always fully illuminated just because of the way the planetary orbits work. But when we sent the Cassini space probe there, this completely revolutionized our understanding of it. And this is just one example. There are so many amazing pictures from the Cassini mission that are just freely available online. This is one of the gaps in the rings, and the rings were always thought to be very, very flat. But when you look at it under a lower sun angle, there are features like this that are casting this really long shadow. Now, we can use exactly the same equation that we used on the moon before, measure the shadow length, measure the angle, we know the angle of the sun, therefore we can calculate the height using that same piece of maths. Now, we always thought the plane of the rings was just a couple of stories high, about the size of a 2-bedroomed house. But we found that there are lumps in Saturn's rings that are taller than the Rocky Mountains, which nobody was expecting. So it just shows you really do need to send space probes to places to really study them. I love this picture. This was a raw picture that I processed myself from NASA. You can just download these images. The whole of the edge of this ring is covered in features that are casting these long shadows. Now, yes, this is a low sun angle, so the length of these is slightly exaggerated, but you can do the maths to calculate it. And this is why we know that these things are as tall as the Rockies. This is a small moon called Daphnis, one of the shepherd moons in Saturn's rings. And basically the ring is just hoovering up material here and leaving these empty spaces. But also there are these edge wave shadows as well. And these are features that are much, much taller than the surrounding area. And one more picture here. This is Saturn's moon Nemus, which looks like the Death Star. It's got that kind of big crater on it that makes it look like the Death Star. A really long shadow cast by the moon, but also more of these jagged shadows from the edge of the rings. So looking at the shadows on these rings has basically completely changed our understanding of the structure of them. Just a very quick picture of comet Churyumov-Gerasimenko, which had a space probe, Philae, landed on that comet a couple of years ago. I was in tears when it happened. It was just amazing. Seeing the comet under a different lighting angle shows cliffs, it shows craters, it shows scarps and tunnels, and unfortunately, Philae didn't land as it was supposed to. The landing harpoon didn't fire properly, so it bounced off and rolled into one of the shadowy regions and therefore lost power. So there was a cartoon of the little thing getting a blankie and going to sleep, which made me cry all over again. But seeing things from these different lighting angles totally changes how we see them. So I'm just going to finish quickly because this is an important thing when you are looking at shadows, and that is something called pareidolia. And this is where a psychological phenomenon causes people to see patterns in something that is actually very random. And very often with humans, that leads to people assigning human characteristics or animal characteristics to objects. Now, I think historically, when in our hunter-gatherer days, this was a useful adaptation because it's better to think you've seen a tiger and run away than to not see the tiger and get eaten. So there was a kind of evolutionary advantage to this, but in the modern day, it just seems really crazy. But there is definitely a kind of human face in this geyser that a friend of mine took the picture of. The famous one of this that I was aware of very young was the man on the moon. This is a sketch I did of the full moon quite recently, and I can never, ever see the man on the moon. I was frightened to death of it as a child, but I could never see it. Somebody on DeviantArt has just enhanced a photograph of the moon to show where the eyes, nose, and mouth are. But even looking at this, when I look at a picture of the full moon, I still struggle to see this face. But I'm somebody that rarely sees shapes in clouds either. But this has led to all kinds of things. Now, obviously, top quality scientific reporting from newspapers like the Daily Express in the UK. But this was people going crazy. Oh, there's an astronaut working on Mars here. This is a picture of the rover and there's an astronaut working there and it's a big conspiracy. They're there and it's a secret. And just no. This picture as well equally made news in the Metro because this looks like an arm and a helmet and a backpack. Just not the case. This is basically what one of the scientific arms looks like on one of the Mars rovers. Now, the rovers are big, but this scientific equipment here is not big enough to basically cause a shadow big enough to look like a human. And this is where the problem arises. When you see stuff on the surface of other planets, you don't have a 1 meter ruler in the field of view to give you scale. You don't have anything to give you scale. You could be looking at a boulder that's 5 kilometers across, you could be looking at something 5 centimeters, you just don't know. So anything that looks vaguely humanoid, people go crazy over. This is one of the most famous situations where this happened. This is the Cydonia region of Mars. You look up here at this guy, looks a bit like a face. And there are these things here that look like pyramids. And this led to so many conspiracy theories. This guy is not new. He was first discovered by Viking 1 in 1976. And everyone was like, oh, there must be ancient civilizations that have lived there and carved humanoid faces. The Mars Global Surveyor went back and actually did some proper high-res imaging of this region, and basically it's a lava dome measuring 3 kilometers across. So if you was going to do a carving of a face, it would take you quite a while to do it on something that's 3 kilometers in each direction. And it just doesn't look like a face when you see it under a different lighting angle. And yeah, people love these conspiracy theories. There's a woman on Mars. It's difficult to actually find her, but she's there. Just zoom in on that. They did the science on this. She measures literally 10 centimeters or so in height. It's just not a woman. It's basically just some pebbles that have got a slightly different kind of reflectiveness, if you will. Equally, this is a mermaid on Mars. I've had to zoom this right in because basically she's so tiny that she's probably even smaller than the previous one. Like, this is literally 100 pixels across. There is no way this is big enough to actually be a mermaid. There's no water on Mars, so I don't know what a mermaid would be doing there. But even if it was a woman, just too small, way too small. And an iguana, apparently there's an iguana on Mars as well. Yet again, looking at this photograph without any information about the camera or the field of view, this could be a 10-kilometer across sized iguana, or it could be a 2-centimeter across iguana. We just don't know. So it's really important when you are studying shadows that you do so under lots of different lighting angles and that you don't jump to crazy conclusions. So that's the end of the presentation. I hope you found that interesting and learned something. I will stop my screen share, and then if Anne has any questions, we can go ahead and do that.
Well, we're going to test out the recording equipment because we've had some technical difficulties today, but I do have quite a few questions because this is all new information to me. But yeah, I think a couple of things I wanted to sort of verify with you. I'm so glad you touched on the face on Mars because some friends of mine might know when I was doing my doctorate, there does reach a point towards the end where you just need to watch pure and utter trash on TV. And I reached the point where I was watching Ancient Aliens, which is like the cream of the crop garbage, just like pure trash. And one of the things they kept talking about was this face on Mars. And so as you were going through your presentation, I kept thinking, oh, I wonder if she's going to talk about a face on Mars. So I guess one of the things that I'd be curious to know is you talk about this thing called, how do you even say it? Pareidolia. And I was just wondering how challenging is it to get conspiracy theorists to really understand the math behind the work that you're doing?
It's pretty impossible, to be honest. I mean, I've now given up engaging with people like this on Twitter because the kind of flat earth type phenomenon, I find it quite disturbing, the kind of movement towards anti-science at the moment and the mistrust of science when we do so many amazing things. These people don't want to hear the answer that you're giving them, and you end up wasting hours of your time going back and forth, and you will say, yes, but the maths proves this, and they'll come back with, yeah, but what about? And the whole what about-ism in an argument means you're just never going to get anywhere. And so there are a lot I mean, there's some stuff that in my full-length version of this talk, I talk about the cities on the moon that people claim to have found. And they're using photographs that are decades old that basically are so low res that it could be literally anything. And we have high-res cameras in orbit around the moon imaging those same regions, but they're not interested in looking at the new pictures. The new pictures are a conspiracy. They're fake. They're not real news. And so it is almost impossible to actually convince somebody that believes YouTube is a good source for doing research. Whenever anyone comes back and says, yes, but I've seen a YouTube video of, you know that you're wasting your time because YouTube is not a scientific journal. It's not peer reviewed. Anybody can put any video out on YouTube and get a load of views because most people are laughing at them. But once people get into that mindset, it's almost impossible to change their mind, sadly.
Well, I think you're absolutely accurate in that sense. And again, apologies for any of the reverb. Mary and I are actually sitting right next to each other right now, so we're testing out new equipment at the moment. But I guess the other thing I want to learn a little bit about from your end is what are the long-term research benefits that come from knowing this sort of information? You talked about how landing equipment, for example, if you're trying to find a certain part on a planet or an asteroid and you want to make sure that they land relatively safely, how does this sort of information help scientists to navigate a terrain that they've never actually been on themselves?
Actually, because Philae, when we landed on the comet on 67P, it didn't land correctly, and everyone was kind of, well, the people that are not astronomers were like, oh, well, that was a waste of money. But actually, we learned so much in the months leading up to that, because we put a space probe in orbit around that comet and followed it as it made its journey in closer to the sun, and that's when comets kind of have their activity. And also the fact that it didn't land properly didn't matter, because it bounced, and then it bounced several times, and we had basically kind of seismology equipment measuring the bounce. So we knew a lot about the composition of that comet based on how it bounced. It wasn't supposed to bounce, but we still got good science from it. And I've been to several talks from the teams involved with that landing mission, and we learned so much about that. Comets are a bit of a mystery. They very often, comets are leftover material from the formation of the solar system, and some comets come from really far out, like way beyond the outer edge, like on the Oort cloud is kind of theorized but widely accepted to exist, and we're talking way beyond the orbit of Pluto here. This stuff may have had some kind of gravitational knock that knocks it into the solar system. It's never been into the inner solar system before. This is material that is completely pristine and untouched from the formation of our solar system. So we have a lot of theories about what the material that the solar system was made from looks like from meteorites that we've studied. But having a comet that is pristine and never seen before can tell us so much about material. Comets, some comets are periodic, and they kind of, like Halley's Comet, for example, every 76 years will come in and go out. Comets that have done that loads and loads of times throughout their life will have undergone many chemical changes because of the sunlight. So a comet that is coming from way further afield won't have had that. So we get a really unique opportunity of studying pre-solar kind of material, which is vitally important for understanding how the formation of the solar system took place. And that's true with all of the stuff that we do when we look at Saturn's rings. I mean, it's really mysterious when Saturn was thought to be the only ringed planet. What's going on? Where did they form? Why do they look like that? And knowing that there are bits in there that are the size of the Rocky Mountains just blows your mind, because they look so thin and flat and beautiful. And so we just don't get the opportunity to see it under those conditions from Earth, because we obviously have the sun behind there, just the way that things line up for us to be able to see the planets. So it's just so important that we send probes out to study these things. Really important.
Wow. That's so much information. I'm learning so much. And like I said, I continue asking questions, and I probably will once we stop recording. But I think what I'm going to do is end with this last question, which is going to sound trivial in the grand scheme of things, but you used a couple terms. There was a local noon. I don't know what that means. And there was another term that you used called a shepherd moon. So before we finish, could you explain what those two terms mean?
Yeah, noon, the definition of noon or midday is when the sun is at the highest point. Now, if you think like the sun is kind of going from east to west throughout the day, so depending where you are from east to west within the UK, the exact time that the sun is at the highest point will vary. Not by a huge amount, but back in the old days, there was no need to standardize. People just knew local noon because you was out working the land, people were farming. This would have just, every region would have had its own noon. Whereas these days, we're so kind of driven by Google Calendar and needing to know everything to the exact minute, and everything is just standardized. So the exact time, if you measure this, depending where you are, will be a very different time of the day, depending where you are in the UK. So, and you can then use a really simple equation to calculate the time using the kind of measure of shadows. So you can do that just around midday if you go out with a stick, just measure when it's the shortest. You don't need the absolute figures. You can just put a dot on it and see when it's at its shortest. And that will tell you when local noon is for you. And I think it was around about 12 minutes away from noon for us here when we did that. And also bear in mind that if you've got daylight time saving, local noon will be in GMT, not British summertime. So local noon will be around about 1 p.m. in the summer, not 12, because we've moved the clocks forward. Thankfully, they're going back again tonight, which is quite useful. I like the extra hour of sleep. Although many people are saying an extra hour of 2020 is not welcome, but that's another topic. Now, a shepherd moon, when we look at Saturn's rings, initially you would think that it was just ring material, but there are loads of gaps. When you see the rings, there are these kind of big black spaces in between them. Saturn has loads of moons. It has, I can't remember the exact figure, it's about 100 moons, and many of them are really small. And what they are basically very small moons that are within the ring system. And as they orbit around, the gravity of that moon is just hoovering up material from within the rings. So that little picture that I showed you of Daphnis, it's kind of bedded in. The gap in the rings is the same size as Daphnis because as it goes around, it's just sucking up material. So over the next kind of million years, it will get bigger and bigger and bigger, and the gap in the rings will also get bigger. And there are loads and loads of them within the rings, and call them shepherd moons because they're kind of shepherding the material and carving out their own dark path in the ring system. So yeah, until we kind of had much higher res equipment to be able to do that and sent probes out there, then we discovered that Saturn has a lot of moons, and so does Jupiter. So yeah.
My goodness, there's so much information. Really fascinating. And I've got to say, despite all this information, we'd be talking forever. That's it from us at Coffee and Cocktails with your host, Dr. Ann Wand. I'd like to thank Mary McIntyre for her wonderful presentation this afternoon. And if you enjoyed the guest lecture, feel free to leave a comment. Otherwise, this lecture is dedicated to my former colleague and advisor, Professor Marcus Banks of the Institute of Social and Cultural Anthropology at the University of Oxford, who passed away yesterday. That's it for now. Thanks for listening and have a great week.